So, okay, so what we're going to do now is talk a little bit about the endurance limit. Now, we know that there is a endurance limit SE prime, which we computed from a lab tested endurance specimen. Uh, I actually showed that to you. It was, yeah, this specimen gave us SE prime. Okay, so that came from the lab tested endurance specimen. But when you actually take something in the field and test it, it actually fails at a stress different from the stress SE prime. The endurance limit is different. So SE is not equal to SE prime. So the value of endurance in the lab specimen is different from that in the field. And that's because there are various factors which affect or modify the endurance factors. So these factors are as follows. There's a surface factor, size factor, load factor, temperature factor, reliability factor. Each of these factors have a corresponding value, Ka, Kb, Kc, Kd, Ke. And we can actually take these values into this equation and solve for SE. So we we have this value from lab experiments, and depending on how you're using the actual part, you will have a factor which will get multiplied with SE prime, and that would be your final endurance limit. So it's very important to know it because you can just miss it by a whole value, by whole a big value because you don't have these factors. So let's dig through this particular endurance modifying factors one by one. Surface factor. Okay. So when you look at the specimen in the lab, it's highly polished. Okay, it's just perfect, but machine element is not, right? Don't expect it. So depending on the finish, you can find the endurance factor Ka. It is S times SUT raised to B. SUT is the tensile strength, material property, and A and B are constants which comes from the table below. So you will basically figure out what is the surface finish. If it's ground, you will use a factor of A as 1.21. If it is kpsi, you'll use 1.38 if you have MPI, if you have SUT, the MPa, and you'll use the exponent minus 0.067. Same for some other ways in which you finish it. So based on that, you will compute K. So that would be one of the factors. Okay, let's look at the next one. KB. KB is a size factor. Okay, so normally when you do this test, you have a round rotating round specimen is actually spinning. It's spinning because then you can apply the cycles, right? So if it is in bending and torsion, in axial loading, so it won't modify anything. But if you're doing a bending and torsion test, then you need to find the factor kb, and that kb will depend on the diameter and will not depend on anything else. So take the diameter either in IPS or SI units, compute the factor kb, and that sits there. Now, you may have a situation where you're not dealing with a round specimen. That is, the machine element is not round, but is uh, non-round and it is non-rotating. So if it's non-round or non-rotating, then, or even if it is round but it's non-rotating, the key thing here is non-rotating, then you need to uh, basically use a different way of computing it. So what you need to do is you need to use a theory called critical volume theory, okay, which says that the volume of material experiencing 95% of maximum stress is critical. The goal here is to use the critical diameter obtained by equating volume of 95% stress of non-rotating specimen to 95 stress of rotating round specimen. So it seems very confusing, but I think I've simplified this. So what you do is you basically take a round specimen, the area in yellow is the 95% of that, it edges, and then a non-round specimen, non-rotating specimen, the stress is again the area which is shown, which is by this theory. And so you basically equate the stress of the round specimen, 95% area, with the stress shown in the bottom one, and use that to figure out an equivalent diameter. That's what is done. And that basically gives you this T. So you don't have to go to the details. This is what is computed from the yellow shown here. This is what the value is computed from the yellow shown here, and you equate the two to compute the equivalent diameter. So this D in C is equated to this to get this formula. If you have a rectangular specimen, use a similar theory of the 95% theory, and then you compute an equivalent diameter here, which depends on height and width. And then this equation is then used in here. So you see that the equation for D, that comes from uh, here. So this is for rotating specimen. So you're sort of taking a non-rotating specimen, converting that to a equivalent round section, and once you have a round section, you're then mapping it to as if it is rotating. It's kind of confusing, but hopefully when you do the problems, it'll be more clear. So you need to figure out under what conditions the machine element is used before you apply any of these things. Okay, that's KB. Okay, next is KC. KC is loading factor. By the way, this is also for KB. This is not for KC. This is the same formula that I wrote down, but this is for different. So I only wrote down for this one, 0.370D. It is 0.370D, but this actually gives you for, well, these are the two ones I wrote, but these are for I section and another section which I've not talked about. Okay, the loading factor Kc starts here. This is actually simple. It depends on how you load the machine element. If you load it in bending, you don't do much. You just put 1. If axial, use 0.85. If you start from 0.59. Pretty straightforward. Okay, next is KD. KD is a temperature factor, the effect of temperature. So when you do this test in the lab, you do it at room temperature. But when you do this when the machine element is loaded in the field, it might be subject to a different temperature. So this factor accounts for the difference in temperature between lab specimen and the actual field. So what you do is you compute this ratio, ST divided by SRT. You can see that it only depends on one single uh, variable, that is the temperature. You could either use temperature in Fahrenheit, or if you have Celsius, you could use the temperature in Celsius. You'll compute this ratio. So what is this ratio? Well, it's the ratio of ultimate strength at operating temperature to the ultimate strength at room temperature. So this is the temperature at which you do the lab experiment. And this is the temperature in the field where your machine element is located. Okay, so you do that calculation, find that ratio. Now there can be two scenarios. SE prime is unknown and SE prime is known. Okay, SE prime being the endurance strength of the specimen in the lab at room temperature. Okay, so what you do is if SE prime is not known, you estimate the ratio, which we did here. So let's just say this is step 1. Okay, so yeah, so this is the step 1A. So estimate that from the formula I wrote down here, tilde. Step 2 is estimate SUT at the operating temperature. What I mean by that is this is basically giving you uh, the ultimate strength at operating temperature to room temperature. So you can use this formula. Better way to write this is perhaps this. ST, SRT. Okay, so this thing here has been computed. So the same thing goes in here. So once you have this ratio from this formula, the tilde, you can compute that, and you'll know what the ultimate strength is at room temperature. You can compute the ultimate strength at the operating temperature T. Okay, so that's step number two. Step number three is we estimate SE using these formulas. 0.5 SUT or 100 kPSI. This is a similar formula we had earlier. And once you have that, you can then compute KD, which is simply 1, and SE is SE prime. Now, one thing to note here is uh, this is actually SUT at T. Okay, I should have put it down there. That is, so B and C is connected. You cannot do C without B because you need this SUT at temperature T. All this is at T. Here, T being the temperature at which you are operating the specimen in the field. Okay, so that's the last step. KD is 1, SE is SE prime. Okay, again, I'm going through this very fast, but when I solve a problem, I think it'll be very clear as to how to use this formulas. Okay, SE is prime is known. Sometimes SE prime is known. The steps are: one, you estimate the ratio first. B, estimate KD. KD is simply ST divided by SRT, and then C, estimate SE as KD times SE prime, and then go ahead. Okay, that's the KD, and now let's go to KE. This is the last factor. KE is a reliability factor. It's as simple as looking at the reliability of the machine element which is in the field. Okay. Uh, Hopefully there's a different calculation which tells you that. Once you know that, you can compute KE as follows. So if the reliability is 99%, you'll use a KE of 0.814. If the reliability is 99.999%, then you use 0.620. You could also use it in this different way. You could also use ZA. This is a transformation variable. Put it here and you'll get KE. But really, it's redundant. You could either use this one with this formula, because it's ZA, or you could just directly pull off KE from there. Okay, so that will give you KE. And once you have KBA, KA, KB, KC, KD, KE, you're ready to go with computing the endurance limit. So okay, so as I said, this is really hard to parse so quickly. So what I've done is I've tried to have problems which try to help you figure out how to use this five factors. So we'll solve basically multiple problems.